So the problem is that in a triangle ABC, the in circle is inscribed and three more circles are inscribed in such a way that they are touching two sides of the triangle and as well as the in circle of the triangle. So these are the three circles which are touching the two sides and the in circle. So the radius of these three circles are given to us, like suppose the radius of this circle is 4, radius of this circle is 9, and radius of this small circle is 1. So we need to find the in radius of the triangle ABC. Now let us quickly revise some of the important ideas in geometry. Like let us take the case for externally touching circles, like this circle and this circle, they are touching externally. So our problem will be to find the length of this direct common tangent Mn. So to find the length of the direct common tangent Mn, let us devise a very simple process. That is, we can see that this length is the radius of the bigger circle, suppose R1, and this length is the radius of the smaller circle, suppose R2. So since they are externally touching, so the distance between their center can be calculated as the sum of their radius R1 plus R2. Now from C2 a perpendicular is dropped on C1n, so let us take this angle to be 90 degree, and we can concentrate in triangle PC1C2. So in triangle PC1C2 we can easily write down that the length of PC2 is nothing but square root of C1 C2 square, that is hypotenuse square, minus the base square, that is PC1 square. And PC2 will then come out to be root over C1 C2 square, that is R1 plus R2 whole square, minus PC1 square, that is going to be, like we can see that this much distance is R1 and this much distance will be R2. So PC1 can be written as R1 minus R2. So the length PC2 will come out to be root over 4 R1 R2, that is 2 times root R1 R2. So this is the length of PC2, and you can see from the figure that PC2 will be same as Mn because this is a rectangle. So length of Mn, or the length of direct common tangent for externally touching circle, comes out to be 2 root R1 R2. So this is the very important result that we are going to use to solve this problem efficiently. So let us come back to this problem, which says that let us take the in circle and this particular circle whose radius is given to be 4, and let us consider the center is at O1 and the in center is at O. Now this must be the bisector of the angle B, because B and O is joined, so this must be bisecting the angle B. So this much angle should be half of B, so this is B by 2, and from the center of the circle, this circle O1, we have dropped a perpendicular on ON, which is a radius of the in circle, and another perpendicular is dropped on AB. So this much length should be the radius of the small circle R1, and ON should be the length of the radius of the in circle. Now the length Mn can be written as the length of the direct common tangent for these two externally touching circles. So Mn length can be written to be 2 root R1 using the previous result. This particular result we are using now here. The length of direct common tangent is 2 root R1. And so another important thing is there that this angle is B by 2. So we can claim that this angle should also be B by 2. Because you can see that Bn and O1P, because O1P is perpendicular on ON, so Bn and O1P are parallel to each other, and since they are parallel to each other, so this angle B by 2 and this angle B by 2 must be equal to each other. So in triangle O1OP, we can write down that cot B by 2 will be nothing but base by perpendicular, that is O1P by OP, and O1P is nothing but the length of Mn, that is the direct common tangent, so 2 root R1 divided by OP. So OP can be written as like this: total length is R and this much length will be the radius of this circle R1, so OP can be written as R minus R1. And similarly we can write down cot A by 2 to be 2 root R R3 divided by R minus R3, and cot c by 2 can be written as 2 root r2 divided by r minus r2. Now in a triangle ABC, as we know that since a plus b plus c is pi, so there is an important identity, trigonometric identity that we can use, that is cot a by 2 plus cot b by 2 plus cot c by 2. So this sum comes out to be cot a by 2 into cot b by 2 into cot c by 2. So this is a very important identity that we can use here, since we know the value of cot a by 2, cot b by 2 and cot c by 2. So let us substitute the values out here, like cot a by 2 can be substituted as from here, and let us substitute the value of r3 from the figure to be the r3 we have taken to be 1. So substituting r3 to be 1, cot a by 2 will become 2 root r divided by r minus 1 plus cot b by 2. For cot b by 2, substituting the radius r1 to be 4, so it will become 4 root r divided by r minus 4 plus cot c by 2. For cot c by 2, let us replace r2 by 9, so it will become 6 root r divided by r minus 9, and that will be equal to the product, that is 2 root r divided by r minus 1 into multiplied by 4 root r divided by r minus 4 multiplied by 6 root r divided by r minus 6. So 1 root r can be safely cancelled out from both the sides, so that will give us an equation taking LCM r minus 1, r minus 4, r minus 9. So taking the LCM, the numerator will come out to be 2 into r square minus 13r plus 36, multiplying the factor, and 4 into r square minus 10r plus 9 plus 6 into r square minus 5r plus 4. So this is going to the numerator, and on the other side we are getting the numerator as 48r divided by the same LCM as the LHS. Sorry, this is going to be 9. So this denominator gets cancelled out, being the same denominator. So we can write down any quadratic equation that will be 12r square minus 144r plus 132 equal to 0. And on simplifying this quadratic, it will become r square minus 12r plus 11 equal to 0. So this will give us two possible values of r, 1 and 11, but 1 is not a permissible value because the least circle is having the radius 1 unit. This circle is having a radius of 1 unit, so we cannot take the radius of the inner circle to be 1 unit, so the answer is going to be 11. So radius of the inner circle is 11 unit.